Hello, Math 120, and this is Professor Gonzalez, and I would like to go over some problems from homework section 6.8. Now, 6.8 is taking a look at the complex number system, how to simplify imaginary numbers, something we haven't been able to do before. And let's get on with that. I think what I want to do first is adjust my chair and also take a look at some of the properties of this section. Let's go down to this some of these definitions. And yeah, let's take a second to talk about the situation here. And here's the situation. So far, if we saw a number that had a square root, right, a square root that had a negative under the radical, like the square root of negative 16, so far up to this point we said not a real number. Not a real number. But now we have to cross that out because we're going to define this as an imaginary number. And so we are going to be able to deal with this. Okay, so that opens up the imaginary numbers, which opens up the complex numbers. Okay, so I think what I want to do before we actually get into these definitions is actually making sure we understand our number system. Just because, it's kind of good to know where and how these imaginary numbers fit into our system that we already know. So let's start off. Let's see if I can fit all this stuff in here. It gets a little bit tight, so I think I will zoom in. And we will start off with, let's see, get rid of that. We're going to start off with the natural numbers. So natural numbers, also known as accounting numbers, are just literally these numbers that we count with 1, 2, 3, and so on. And they do not include the decimals or fractions in between those numbers. They do not include 0, and they do not include the negative values. The next number system that is, now I'm going to write these as subsets. So the natural numbers are a subset of the next number system that is only slightly larger than it. And the next is called the whole numbers. And whole numbers just gains one element. It just gains 0. So whole numbers are 0, and then the counting numbers or natural numbers. Still no fractions or rational numbers in between, like 1.5 or 1 3/4, or decimals 1.5. And we don't have negative numbers. Then the next number system are called the integers. Integers. Now the integers are going to be the whole numbers. But then we also include the opposites of the natural numbers, -1, -2, -3, and so on. So now we have the whole numbers and then the opposites of the natural numbers, the negative numbers. So we've just increased our numbers by quite a bit. Then we have another, so all these are subsets, right? And so the next number system that's larger, but also the previous systems are subsets of it, would be the rational numbers. So now rational numbers, I'm running out of space already. I should have, well, wait a minute. I do have a tool to move that, don't I? Sometimes I forget that. Just move this on down there. How much space do I have? So we've got these rational numbers. Now the rational numbers are basically the integers that could be written as a ratio or a fraction. That's the first part of it. So you grab any of the integers, positive or negative. So let me give you some examples. Like let's take -5 over +2. Right, that equals 2 goes into 5 2 times, so negative 2.5. Right, but with rational numbers, we like to actually look at their decimal representations. And, whoops. If you take these integers and put them in a fraction form, negative 5 over 2, it equals negative what? 2.5. Now there's something I'm trying to say about these integers or these rational numbers. I think I want to move this little guy up a little higher. There's something I'd like to say about these rational numbers, and that is that rational numbers have a couple characteristics. First of all, when you look at their decimal values, they either terminate. Whoops, what's going on there? And so this is an example of a terminating decimal. Notice it just stops, so it terminates. Or rational numbers, when you look at their decimals, they repeat or have a pattern. Okay, so when you take a look at that, repeat or have a pattern, what's an example of a rational number that repeats? And I have second thoughts about that. We'll go a little bit higher. Something that repeats, how about something like 1/3? 1/3, when we change it to a decimal, look at our calculator, 0.3, and that repeats forever. So that's a repeater. So repeats okay, terminates okay. You might think, well, what's left? Well, there are some numbers out there that do not terminate and do not repeat. They go forever and they don't have any pattern. Also, a pattern would be okay too. Repeating patterns. Repeating patterns. So like if you saw something that had, you looked at its decimal value and it was 0.2424. So there's a block that's repeating, right? Still a repeating, but it has this pattern or this block of repeating. That would be okay too. So these are considered rational numbers. Okay, a number system that actually is going to be now mutually exclusive to these, meaning there isn't any overlap with these numbers. Let's see now. I think I want to move. Good thing I'm able to move this. I'm just having second thoughts about all of this, where it goes. Let's go like that. Now we have another number system called irrational numbers. So irrational numbers are numbers that do not repeat and do not have a pattern. So probably the most famous number of that would be, most people remember pi, because it's approximately 3.141, and it goes on forever. It doesn't repeat, doesn't have a pattern. That's irrational. That's an irrational number. Some other more common ones, like the square root of 2, would be irrational. And even if you had something like, 1 plus the square root of 3, these are all irrational numbers. And when you throw them in the calculator, as a decimal, they do not repeat, they do not terminate, they do not have a pattern. Now these numbers I kind of want to highlight. Let's see, how do I do that? Let's make these green, I guess. So they're mutually exclusive. I just want to make sure that you see that it's not touching the rational numbers at all. Okay, and maybe we'll make the rational numbers red. I hope I don't regret doing this color, because I do want to show that when you put all, what color do I do now? Jeez. Okay, you put all of the rationals and irrationals together. And this makes up a very large number system. So when you put all the rational numbers and the irrationals together, we get the real number system. up to that point, up to this point, that was the largest number system that we had. And now we are going to add to that. We're going to add these numbers called pure imaginary numbers. Whoops, that's not a J. G, imaginary number. Pure imaginary numbers. And pure imaginary numbers, here it is. They are the numbers that have a negative under the square root. So something like negative 16. Now we have a place for it. Before we said, hey, that's not a real number. Well, now we know it is. It's an imaginary number. So we're going to have a way to simplify this down. I'm going to have to define that for us. But this is an imaginary number, and so the imaginary number system, you know, there's many numbers that are imaginary. They just stem from having that negative under the radical, under the square root. And now finally, when I put, what color am I going to go with? Red, I guess. When I put all of the reals, so let me go like this. Man, I feel like I'm doing too much of the same color. When I put all of the reals together with the pure imaginaries, I get the largest number system that we have here. And that is going to be, so once again, when you add, whoops, somehow I'm stuck. Okay. Up, still stuck. Come on. So when you put the real numbers together with the imaginary numbers, you get this very large number system called complex. So the complex number system is the blue that covers reals. What are in the reals? Rational numbers, irrational numbers make up the reals. We got these pure imaginary numbers, which are mutually exclusive with the reals, right? They do not overlap at all. But when you put the reals together with the imaginaries, you get complex numbers. And complex numbers, well, let's just shoot. Gosh, I have these I kind of second guessing myself here. I think, let's make that yellow. So complex numbers come in the form a plus bi, and that is to say that this a value is considered the real part, and this bi is considered the imaginary part. Geez, there we go again. Imaginary. I cannot spell. Well, at least I'm catching myself, but dang, I know a G goes there, but I seem to want to put a J because it sounds like that, I guess. But anyhow, a plus bi is our complex form for complex numbers. And so you've got the real part and the imaginary part, all right? So that gives you a good overview of what's going on. But let's now, we need to talk about how this works. And now that we have that background, let's see. It says we have a definition for the imaginary unit. The imaginary unit is denoted by an I, is the number whose square is -1. That is to say that whenever you see an I squared, you can replace it with a -1. Okay, but that's not really the first thing. Let's see, I think the first thing I would want to show is that the principal square root for a negative under the radical is that if you have the square root of a negative number, it will simplify out to the square root of that number times I. Okay, in other words, another way to kind of say that that sometimes makes decent sense is when you take the first fact up here, when we say I squared equals -1, if you come along and square root both sides of that, we would then get, right, squaring a square root gives us the radicand inside of I, which equals the square root of -1. And you could kind of now see that from this second fact, which is, that's what this is saying right here, actually, right? That -1 right there, use another color, that -1, I'll use in green, and the square root of the negative just comes out as an I. Okay, and then to tie it to the number system I was just talking about, to tie all that together, when you take a look at the complex number system, complex numbers are of the form, as I said, I'll try to use the same color that I had before, and darn it, I've got to go up there to get that. We've got this real part that I showed you down here, A, where A is the real part, and what is it? BI is the imaginary part. So the number B is the imaginary part of this. Just to be clear though, BI is the imaginary part, but A and B by themselves are real numbers, but that BI makes it a pure imaginary part. Now it's not pure when you have so let me go back a second. If you just have a number that is, let's say you had the square root of -25, and so we know that is, we could break that down to think of, okay, we got a square root of 25. We also have that square root of -1. Oh, wait a minute. As we said, the square root of -1 is just I. So we got to get used to replacing the square root of -1 with I, and we know the square root of 25 is just 5. So we get 5i. Now, because there isn't a real part attached to that, this would be called a pure imaginary number. But these pure imaginary numbers are still part of the complex number system, because we could attach a real number to that. We're just being a little tricky. We're putting a 0 in front. Oh, now it's A, the real number 0, plus the imaginary part, which is 5i, right? So we could write any number. We could write any number as a complex number, right? -2 could be simple, right? You can write it as a complex number. The real part is -2. The imaginary part is 0i. Okay, so anyways, complex numbers systems is the biggest. We better get going. It's getting late, and I haven't even started the homework. Let's get up here and get this party started here. So what do we got going here? Just to start it off, well, with all that background, hopefully this helps. It says, state whether the following statement is true or false. All real numbers are complex numbers. Dang, I've already got to go back. All real numbers are complex numbers. Well, let's see. My real numbers are in the middle here in the green, so all real numbers are complex numbers. Yes, all real numbers are complex numbers because real numbers are a subset of the complex numbers. So that is true. Let's go back there and say true, but we got to pick something. There's two truths. Is this one or this one? True. The first one says because the real number system and the complex number system are the same. No, that's not true. Must be this one. We better read it. True, because the real number system is a subset of the complex number system. Ding, ding, ding. That is the answer. All right, so just to kind of, now you can get faster at this, but just to kind of break it down so you can see what's happening maybe a little better. I'm going to think about this as the square root of 4 and the square root of -1. So we know square root of 4 is just 2. And we know that the square root of -1, what do we need to do with that? That just is replaced with an I. And that's defined by the imaginary unit and also by a principal square root of, what it was called, the principal, where I'm at, the principal square root of a -n, right, denoted as square root of -n, kicks out as the nth, the square root of n times I. All right, so let's do the next one, and you probably don't have to write it down, but it's not bad to write down the square root of 7. We got the square root of -1. Well, square root of 7 is not going to simplify, but we do know that the square root of -1 is just going to be I. So we just get our answer of square root of 7i. Now, I want to tell you something. It is really, really easy to get sloppy with that square root and put the I in under the radical sign. And if you do that, and I tested that with MyLab, and I was happy to notice that they marked that wrong, and they should mark it wrong. But it is a little bit frustrating in a computer because it's such a small. What you have to do is when you're on the inside of the Radican, you have to hit the right arrow to get yourself out of the Radican, and then you have to put the eye on the outside. So that's something that you'll probably be frustrated with a couple times. And you have to just get used to that, and it's better to practice now than on the test, right? That eye has to be on the outside of the square root. Well, what about this guy here? Let's zoom in here. Well, I see that negative under the square root, no problem. If I could write 28 as a perfect square, and I think I can, how about the square root of 4 times the square root of 7, and I've got the square root of negative 1. Okay, so square root of 4 is 2, square root of 7 does not simplify, and I know negative 1, square root of negative 1 is just, whoops, what's going on here? I know the square root of negative 1 is just I. And so there we go, got it. Once again, remembering that I see a square root of negative 1, I'm going to put an I, substitute with an I. 64, okay, so we've got 5 plus, but 64 is really where it's at. So square root of negative 64, I'm thinking in my head, the square root of 64 is not a problem. It's this negative square root, negative 1, the negative symbol. So I know 64 is 8, and the square root of negative 1 is just going to be I. So I get 5 plus 8I. Okay, got to make a little space here. So that gives me 5 plus 8I. Number 6. Well, how about if I simplify it over here? I've got the square root of negative 28. I know 28 will simplify or factor down to a perfect square of 4, so square root of 4. Then I have square times the square root of 7, and I've got the square root of negative I. Square root of 4 is 2, square root of 7 does not simplify out of the radical, and the square root of square root of negative 1 is just I. So I get negative 9 minus 2 square root of 7I. Once again, making sure that that I is on the outside and not under the radical symbol, otherwise it will be marked wrong. Let's take a look at the next problem, which is number 6. And there's all my chicken scratch notes and everything. Number 6, number 7 is next. Okay, ooh, getting a little more complex. Write the expression as a complex number in standard form. So remember the complex number in standard form. The previous problems that we just did, those guys were all what? Probably pure imaginaries. Oh no, that was written in complex. Okay. So up to here, these were pure imaginaries, and the reason why is because the real part, if we had to be technical, is 0, right? So we call them pure imaginaries because you don't have to show that 0 there. So, but then when we get down to number 5, now we have a real part to the 2. And by the way, you cannot add real numbers with imaginary numbers. They stay separate, just as if that was a 5 plus 8x. It is a number, but they are not like number systems that can be added together. You have to keep the real parts first, and then the imaginary. Man, I hate it when that happens. Then the imaginary part comes second. Okay, and same thing here, right? What was the real part? The real part was negative 9. And what was the imaginary part? All that right there. Okay, all right, so that's what's happening here, but now we have a quotient. So what I would encourage you to do is take care of that square root of negative 16. I think you can do that probably pretty quick now. We've got 28 plus, and this guy right here just becomes what? Square root of 16 is 4, and that negative under the radical just gives us an I. Okay, now this is over 4. Now, on previous problems, factoring out was the way to go, was the preferred way, factoring out common factors and then reducing. But with a complex number form, complex number in standard form, remember, we want that to be an A, the real part, plus B, I is the imaginary part. So what we really want to do here is we really want to just write them as two fractions. And what we really would like to do is put our I right there. Okay, so this would be 28 over 4, and then we have 4 over 4i. Just to let you know, I did double check it by inserting the answer, having the I up top here, because technically that's still mathematically correct. And they said they let that go. They said that was fine. But the form really would like us to write that I right there. So we essentially have a real number and a real number times I, which makes it imaginary. So here we go. We have 28 divided by 4, which is 7. And we have 4 divided by 4, which is 1. 1 times I is I. So there is our complex number in standard form, 7 plus I. All right, number 8. Number 8. All right, maybe we do a little work over here. Square root of negative 8. That's the square root of 4 times the square root of 2. 4 times 2 is 8. Oh, don't forget about the negative under the radical. So square root of 4 is 2, and then root 2i. Okay, so that's what we've got to work with here. We've got 2 plus 2 root 2i all over 10. Okay, well, let's break it down here. We've got 2 over 10, and we've got 2 root 2 over 10i. Simplify it. 2 goes in 2 once, 2 goes into 10 5 times. So that gives us 1/5. And 2 goes into 2 once, and 2 goes into 10 5. So that is square root of 2 over 5i. There you go. This is 1/5 plus the square root of 2 over 5i. Now adding complex numbers is a breeze. It is just like adding like terms, as if this was 7 plus 7x plus 8 minus 5x. You do it exactly the same way that you would do it when they were polynomials. Just add like terms. Okay, well, that's the way it goes. You add the real and the real parts, and the operator's right there, adding them, right? So we take 7 plus 8. So 7 plus 8 is 15. And then we've got 7i plus, don't forget the sign, negative 5i, which gives us 2i. So we've got our real plus our imaginary part, which gives us our answer of 15 plus 2i. Done. Now remember when we subtracted polynomials, remember I said that people make that mistake quite often, so it's a good idea to distribute this sign and go from there. So negative times 7 is negative 7. Negative times a negative 7 is positive 7i. So I would use those two real numbers or complex numbers, that complex number rather. And now you just add like terms. So we've got 5 and a negative 7 is negative 2. And we've got a 5i and a 7i, which is going to make a plus 12i. Now, yeah, you could factor something out, but they don't really need us to factor it out. They don't want us to factor out because we're trying to leave this as a complex number in complex form, which is a plus bi. So we're leaving it like that. Negative 2 plus 12i is the answer. Then we go to number 11. Number 11, a little more complicated, but, you know, we should just do a sub problem over here. What we should do is, what color should I use? Something different. Let's take a look at this guy. Well, you know, that's probably not all that hard. You could just do that in your head, couldn't you? If it was negative 36, we know that that's square root of 36, square root of negative I. So we got square root of 36 is 6i. Probably could just do that one in our head, 6i. So now we've got 1 minus 6i minus 5 plus. And what's this one going to be? Might as well use the same color because they're going to have to add like terms. And this is the square root of negative 64. Well, the square root of 64 is 8, and that negative means it's imaginary. Okay, now do not distribute or FOIL or whatever you want to call it. People make that mistake. because sometimes students will see these parentheses and they just get goo goo gaga or something. There's something about the parentheses. They just want to start multiplying things like crazy. We know you're not supposed to multiply this because it says subtract. It doesn't say multiply, it says subtract. We also know that with binomials in this kind of situation, subtracting, that negative sign sometimes gets lost, especially with the second term or the imaginary part. So we just go ahead and distribute that and work with those numbers. So we've got a negative 5 minus 8i. And now these are the numbers that we're going to use to combine like terms. We got the real part. Real part of 1, a real part of negative 5. This is negative 4 is a real part. We've got a imaginary part of negative 6i, an imaginary part of negative 8i, which makes an imaginary part of minus 14i. And that is our answer for number 11. Should be negative 4 minus 14i. Okay. All right, well, this one maybe a little bit tougher. We need to do a little bit of, how about work on the side? Let's go ahead and take a look at this guy and work with it over here. That's square root of negative 50. I got a lot of space over here. So square root of negative 50. Well, I'm thinking a perfect square in there is square root of 25. So 25 times 2 is 50. Don't forget that negative. So when we simplify this, square root of 25 is 5. Square root of 2 doesn't get to come out. And I is replaced, takes care of the negative under the radical. So this guy right here is 5 root 2i. This is now 5 root 2i. And this one over here, well, we need to work on that also. Negative, so that's the square root of negative 98. And the square root of negative 98, let's see, 49 times 2. Okay, awesome. So this is going to factor down to the square root of 49 times the square root of 2. That makes 98. And of course, the negative is not a problem because we have 7 square root of 2. And that negative under the radical becomes I. So this now replaces the square root of negative 98. 7 root 2i. 7 root 2i. Let's go ahead and fill in everything else here. There's 1 minus that. Over here we had a negative 4 plus that piece. Okay, we're ready to do this. So you can only add or subtract real parts. And I've got a real part of negative 4 and a real part of 9. Negative 4 and 9 makes 5. And then I go to my purple and I've got an imaginary part of 5. It's not just imaginary, well, it's imaginary, but also in order to put this together, we also have square root of 2's that are the same. So it's really square root of 2i that also must be the same. So we've got 5 of these nasty square root of 2i's, and we got negative 7. Don't forget that's a negative 7 of these square root of 2i's. So 5 and a negative 7 is negative 2. Nasty square root of 2i's. And there's your answer. That was number 12. 5 minus the square root of 2i. 5 minus 2 square root of 2i, rather. Number 13. Okay, something different. Multiply. Okay, well, when we multiply, remember, we have to distribute through or over the parentheses. So we've got, now you might ask, well, can you multiply real number and imaginary? Yes, you can. Just as if you could, if this was 5x times 3 minus 8x, right? I'm using the same coefficients. You could definitely multiply that, and it's just 5 times 3 is 15x. And then we've got 5 times negative 8 is negative 40x. So back then it was not a problem. And similarly, this has a very similar feel to it. This is just an example, so don't think, maybe I just get rid of that. Well, that is just an example. Okay, now here, I need to move it out. Let's get it out of here. It's too close. People are going to say, wait, how does this relate to the problem? It's just an example that if you treat these complex numbers very similarly to what we do with binomials, I think you'll feel a similarity there and it'll be familiar and easier to do. So we multiply 5 times 3, which is 15, and don't forget that I, 15i. And then we've got 5 times a negative 8, which gives us negative 40. And then don't forget I times I is I squared. So now this comes into play, right? The first piece we were using a bunch of is that a negative under the square root is going to be I. But the other sort of piece to that is to realize if I square both sides, what do I get? I get another very useful fact. Squaring a square root gives me negative 1, and I to the second power is just I squared. That's a very useful fact because when I see this I squared, these guys show up, and I just simplify them down to negative 1, which does simplify the number quite a bit, right? So instead of that I, I'm going to put a negative 1. So now we've got 15I minus 40 times a negative 1. Well, we got 15I, and this, you need to take the sign though. Negative 40 times a negative 1 gives me a positive 40. Now that is great. The only problem is it has the real part, it has the imaginary part first, and it has the real part second, and that's not how our complex form is. So all we have to do is just make an adjustment. The real part is 40 plus the imaginary 15I part. And there's your complex number, 40 plus 15I. Okay, now we're getting into it. And this section has 24. You probably saw that and your eyeballs popped out. But, you know, these are not long problems like rational equations were. You know, these are much quicker little problems. So anyhow, we are going to distribute in an extended fashion, also known as FOIL. So we're going to say 4 times 4 is, what is that, 16? Maybe I'll put it over here for space. Let's do that. 4 times 4 is 16. If I get my pen to work, 16. And then 4 times I is just going to be 4I. And let's go ahead and use different colors. 6I times 4 is going to be 24I. And 6I times I, well, that gives us 6I squared. Well, we know that this guy just is replaced with a negative 1, right? I squared is replaced with negative 1. So what is 6 times a negative 1? Well, it's just a negative 6. So let's see. What can I put together? Well, the real part that I'm seeing, the real parts are 16 and negative 6. Well, that's just going to give me 10. And the imaginary parts I'm seeing right here in the middle. And that is 4I plus 24I, which is going to give us 28I. And that is the number. We multiplied it and then simplified it and then combined like terms. So those were the steps of that. That was number 14. Should be what? 10 plus 28I, number 15. Let's do it again. So we've got 4 times a negative 3, which gives us a negative 12. Then we got 4 times a negative 5I. So 4 times negative 5 is negative 20I. And then we'll use another color. 7I times negative 3 is negative 21I. 7I towards, and then we got 7I times negative 5. So 7 times negative 5 is negative 35. And don't forget we have I times I, which makes I squared. So we have this great opportunity. We know I squared is replaceable with negative 1. So 35 times negative 35 times negative 1 is just a positive 35. Helps us tremendously on simplifying a real part of negative 12 and positive 35 is going to, at negative 12 and positive 35, that's 23. So that is just 23. And then let's take a look at these imaginary parts. A negative 20 and a negative 21 is going to be minus 41I. And that is going to be my final answer, 23 minus 41i. Okay, well, that's our old friend right there, right? Remember that guy? Remember? Use this quite a bit on the last couple sections. A plus b perfect square. You can go ahead and multiply it out and FOIL it out if you want, but we do know that every dang time it's just going to be the first term a squared plus 2 times the first term a times the second term b plus the last term b squared. And that just saves a lot of time for us. Let's do it. The first term of 5 is squared. The middle term is just going to be plus 2 times the first term 5 times the second term 8i plus the last term 8i squared. Okay, now we just have to simplify. 5 squared is 25. 2 times 5 is 10 times 8 is 80. Of course, there's an I there, so 80i. And we know that this is going to be 8 squared is 64. We have this I squared. We remember that I squared, we can substitute in a -1 for I squared. And so 64 times -1 is -64. And so that helps us right along with simplifying. We can see that we have those two real numbers there. What's this number, 16? So you have those two real numbers. We have a 25 and a -64, which makes -39. Which makes a -39. Plus, well, let's take a look. Well, it was already simplified for us, right? It's just right there, plus 80i. And that was simplified for us because we elected to use our special little formula. There's the answer, -39 plus 80i. Let's go on to the next problem. Okay, so here's something that I really do want to highlight, that earlier on when we had the product rule, we said the nth root of a times the nth root of b equals the nth root of a times b. We're going to be really tempted to use this here, but don't do it, because the caveat with this formula is that note with the formula, well, the square, in order to use this, not really formula, this is the product rule. In order to use the product rule, well, square root of a and the square root of b must be real. And the negative under the radical means they're not real. So you cannot just multiply these guys up and get a negative times a negative is positive 576. And then the square root of that is, I think, 24. 24 is the wrong answer. Doesn't work. So don't do that. Instead, what you have to do is simplify these non-real numbers. Well, we know, and you can take an extra step if you want to take an extra step, and that extra step would just be realizing that 16 is a perfect square, and also realizing that square root of -1 is just I. So square root of 16 would be 4i times, and of course the square root of -36, well, that's just going to be what? 6i. Now 4i times 6i, now this is something we can multiply, and 4 times 6 is 20. What happened? Whoops, not working. Interesting. I've got that selected. Oh, it's freezing up on me. It's a brand new expensive iPad Pro. Come on, what's going on here? Are we good? Apple, come on. 4 times 6 is 24. No, we're not good. This is not working. Okay. It likes green, but it doesn't like the color of black there, the black pen. So let's see, let's try again. 4 times 6, zoom in, 4 times 6 is 24. We're back in business. 4 times 6 is 24. And I times I gives us this I squared. Now we know that I squared, we can replace I squared with what? A negative 1. And negative 1 times 24 is just negative 24. So the answer is negative 24. So that's something you got to be really careful with. Knee-jerk reaction is probably just to multiply those radicans, even though they're negative, and you're going to get the wrong answer. Okay, now the operation is divide. Now I want you to think back to when we had to rationalize the denominator, which is just a couple sections ago. Remember rationalizing the denominator, where if you had the square root, if we had like 5 over the square root of 2, what I said was be very aware that that's a square root. And if the strategy is, if I want to divide by this square root, really what you do is you want to rationalize the denominator. And square root means you need 2, and you only have 1 2. So we multiply the denominator by the square root of 2, and because it's a fraction, to keep it equivalent, the numerator by the square root of 2. And we've just rationalized the denominator. We have 5 root 2 over 2, right? Square root of 2 times square root of 2 is square root of 4, which is 2. Okay, so that is not this problem, so I'm going to move it, but I think it really has some similarities to that. So if we could always go back to previous learning, it could be helpful for us. And so once again, dividing these complex numbers, we want to put our final answer in complex form. What is complex form? We want to say A plus BI, where A is the real part and BI is the imaginary part, right? So in order to do that, we need to basically get rid of the I on the bottom, is the strategy that I like to think about. So the question is, we're going to multiply this fraction. Whatever we multiply the top, we must multiply the same on the bottom. Otherwise, we will destroy the equality of that fraction. But I can see the key here is to remember, let's put it over here. The key is to remember that I squared equals what? I squared equals negative 1. So if I can make an I square with this denominator I, it'll become just negative 1. And so there's the goal. There's the strategy. Let's multiply the numerator and denominator by I, and let's see what happens. Here's what happens. Down below, we have 8i times I, which is 8i squared. And you can see, I might as well just continue so you can see what's happening. Just like what I wanted to happen, I can replace that I squared with negative 1. And now we have 8 times negative 1, and I've got negative 8 in the denominator. Good, good, good. So that's helping me divide this complex number up top. I must distribute I times 9 is 9i, and I times I is I squared. And once again, I know I squared, so I'm going to write down 9i, and I know I squared could be rewritten as just a negative 1. All right, so we are getting somewhere, but remember, we want our real numbers first and our i's second. So I'm just going to do a little switcheroo in the numerator. I'm just going to have a negative 1 over negative 8 plus a 9i over negative 8. And remember, the form really prefers us to put this I out here. Like I said before, I'm going to say it again. I tested it, and MyMathLab was okay with the I there. But really, the form says, let's put it way out here. They mean the same thing mathematically. Let's finish this guy up here. So negative 1 over negative 8 is positive 1/8. And having a negative down here is technically correct, but we'd rather put that negative out in front. So this was what? The first division problem. This is number 18. The answer is 1/8 minus 9/8 I. And this business that we just did right here, right, the negative popped up there, just kind of want to maybe reiterate for you with fractions. that negative 1 over positive 2 is equal to 1 over negative 2, right? Negative over a positive is a negative, and a positive over negative is negative. Those guys are equal. And in fact, if we wanted to write it out front, we could write it like that as well. That's basically what we did. We took the negative down in the denominator and we put it out front. That's essentially what we did there. And that's something you could always do with fractions and negatives. The thing that you do not want to do, every once in a while someone will do, is they'll see the negative out front here and they will put a negative on top and bottom. Well, then you just made the whole thing positive because a negative divided by negative is positive. So you don't want to do that. Number 19, same strategy. I need to turn that I into a real number, basically. And so I know if I multiply by I will get I squared, which is just going to be a negative 1 in the end. 7 times I is 7I squared. Up top, distribute. Negative 7 times I is negative 7I, and I times 3I is plus 3I squared. Well, let's clean up our I squares. We can replace our I squares with negative 1. So now we have negative 7I plus 3 times negative 1 over 7 times negative 1. Now I guess I'll keep on going this way. Now I've got negative 7 minus, right? 3 times a negative 1 is negative 3, and 7 times a negative 1. What happened to my I? Oh, there it is, yep, right there. 7I. 7 times negative 1 is negative 7. And now let's just put it in the proper form. We know the real part of negative 3 over negative 7, the real part has to go first, plus, and then negative 7 over negative 7, right? I'm just copying, basically I copied the, basically I copied these guys, right? They gave me that. And then the denominator's doing double duty, right? Then I did 7, negative 7 over negative 7. And then don't forget the I. Okay, well, we're almost there. All we have to do is reduce. Negative over negative is positive 3/7. Negative over negative is positive 1I, so it's just I. So the answer is 3/7 plus I. 3/7 plus I. And what do they have in store for us next? Divide. Okay, yes, this is definitely different. Now the thing I want you to go back to and connect with in the past is this little gem, which was A plus B times A minus B when multiplied gives us A squared minus B squared. And we use that extensively to rationalize the denominator. We called it the complex, or we called it the conjugate rather. And in this case, we're going to do the same thing, but we're going to call it it's called the complex conjugate. Complex conjugate. And what is the complex conjugate? Well, you see how we have 9 plus I? The complex conjugate is, you guessed it, 9 minus I. And why is that so important? Because that is basically just the difference of two perfect squares is what it will multiply out to. And then you'll see what happens. Of course, multiply the numerator by that same quantity. And here we go. Let's focus on the denominator because that's where all the magic is happening. Remember, it's the difference of two squares. You can multiply it all out, but we know if you do this 100 times, 100 out of 100 times, the middle terms will zero out. And we're left with 9 square minus I squared. So we save ourselves a lot of time if we just believe that. Okay, now up top, 4 times 9, 36. And 4 times the negative I is minus 4I. All right. Keep it going. Down below, the magic happens, right? 9 squared is 81. And we also know that this is just going to be, in the end, this is just going to be an I squared, which means it's just going to be a negative 1. Now, don't forget that you already had a minus sign right there. And now we're going to put in, now we're going to sub in, this is where a problem could happen, right? Not realizing there is a double negative there, and of course, double negative, we're just going to add them up, so the denominator is going to be 82. Up top, well, up top we still had 36 minus 4i, so we still have 36 minus 4i. Wants us to write this final answer as a complex number. Whoops, what the heck was that? Every once in a while, I just can't seem to write. Complex number, we want to put the real parts together. So the real part is 36 over 82 minus our imaginary part, which is the real part of the imaginary. Okay, that gets complicated, but 4 over 82 with that I is our imaginary part. Now I see a common 2 at least with these fractions, so I think there's going to be some reducing here. Let's go ahead and show that 36 divided by 2 is 18, and 82 divided by 2 is 41. So I'm going to go with 18 over 41, unless I could reduce that more, and I don't think so. And I can see 2 goes into 4 2 times, and 2 goes into 82 41 times. So I get 2 over 41, and I can reduce that more if I can, but no, I can't, so that's good. There's my final answer. So, you know, I reduced it once, and if I didn't get all factors up here up top, you know, you can reduce again if it has more common factors, but a 2 and a 41 do not, and an 18 over 41 do not. So that is my final answer. 18 over 41 minus 2 over 41i. We're getting there. How many more? 4 more. Whew. Okay. Complex conjugate, right? Complex conjugate. 4 plus 6i over 4 plus 6i. And these do get a little bit hectic. The bottom's not a problem. It's that way because we selected that, right? It's just going to be the difference of 2 squares, so it's going to be 4 squared minus 6i squared. That was great. Up top, not so much. 6 times 4, 24. 6 times 6i is 36i. Then I've got 4i times 4 is 16i. And then I've got 4i times 6i, which is 24i squared. We definitely have some simplifying to do here. So let's do it. Down below, we are going to have, what's that, 16 minus 6 squared is 36. I times I is I squared. So might as well just write that down. Well, we might as well go ahead and simplify that. We know that that is going to be a negative 1. And so we've got 16, a negative 36 times a negative 1 gives us a plus 36. Up top, yeah, there's some nice stuff happening there too, because that I squared also can be replaced with negative 1. So this term right here of 24 times negative 1 is negative 24. Well, that's pretty nice, because a negative 24 and a positive 24 just zero out. And then what else do I have? Blue. How about if we combine these guys right here, these pure imaginary parts right here, which is going to be what? 36i plus 16i, which gives me what? 52. 52i. Oh, yeah, that was nice. The real parts just vanished. They zeroed out. Down below, we can definitely add that up. So now we got 52i up top. And what is 16 plus 32? Wasn't that the same thing I just did? 32 plus 16 is 52. And of course, 52 divided by 52 is 1i, so it's just I. All that, and we just got I. How nice was that? Okay, 21, 22. 22, complex conjugate again is going to be the way to go. 1 minus I, complex conjugate 1 plus I. Don't forget to multiply the numerator by that same quantity. And here we go. Down below, 1 squared minus I squared. That was awesome. But up top, not so much. 11 times 1 is 11. 11 times I, that's not too bad, plus 11i. Keep it going here with the green. 3i times 1 is just 3i. And 3i times I is 3i squared. Okay, now down below, 1 squared is 1 minus I squared. Up top we got that I squared, so we're going to replace I squared with negative 1. Let me just write down what I have then. I've got 11, combine these guys right here. That's 11i plus 3i, which gives me 14i. And don't forget this last term, which was 3 times the negative 1, which is minus 3. Now we can combine our real parts of this complex number. 11 minus 3 is 8 plus 14i. Of course, we can replace I squared with a negative 1. Be careful of the double negative, please. Negative and negative makes a positive, so this is 1 plus 1 plus 1 is 2. And we are getting there. Now let's get it into our proper form of the real part, 8 over 2, plus the imaginary part, which is 14 over 2i. Those are fractions that definitely could be simplified down to 4 plus 7i. And we are done with that stuff. One last trick you've got to learn. Find the power of I. These are problems. We have 23 and 24, which are giving us problems that have I to a very large power. Now, if you've seen this before, some books will do this in a way showing that, like I squared equals negative 1, I to the third, right? You can break that down. In fact, a good way to break this stuff down, just if you get stuck, is to always go back to this first rule that I squared equals negative 1. So if you had I cubed, you can be tricky and think of that as I squared times I, right? Well, I know that I squared equals a negative 1. And what's negative 1 times I? That's just negative I. So, so what happens is some people will have this memorized. I squared is negative 1. I cubed is negative I to the fourth. 2, 3, 4. I to the fifth. And then what's going to happen is this is actually a cycle. I to the sixth will just be a negative 1 again. So this cycle will happen all over again. And so you divide by 4, and that's a way to do it, but you have to kind of have some things memorized. So I tend to just teach it this way, this whole idea that if you're kind of clever on how you break down that power, and also using this fact, right? And we have to use that fact all over the place. So that is a very common fact to remember. I squared equals negative 1 because it's one of the basic pieces of complex numbers when we're simplifying. So that usually gets drilled into our head. So even if you're, months out, usually we could say, okay, let's be really clever how we write this. How about if we write it as an I squared because I know that that simplifies down to something nice like a negative 1. And so let's see. Remember we have a power raised to a power we multiply, right? So 2 times what gives me really close to 53. 25, 2 times 25 is 50. 2 times 26 2 times 26 is what? 52. So that's 52. I need one more, gives me 53. So I have to make sure that this equals this, and it does, because once again, 2 times 26 is 52. I to the 52 times one more is I to the 53. But even though this may have felt painful, something nice is going to happen. We can replace that I squared with -1. And you probably know that a negative raised to an even power is going to be +1. So the answer is just I. Let's do that again with our last problem. Let's see if we get I again. I don't think so. Let's see what happens here. Let's be clever about this, realizing that I squared is sort of the key, and raising it to a power. So 2 times 25 is 50, 2 times 26, 2 times 27, 2 times 27, 2 times 27 is what, 54? So one more I makes 55. And you guessed it, we know that we can replace I squared with a -1. That's raised to the 27th times I. Now when you take a negative and raise it to the 27th power, it's an odd power, which is going to make this remain -1. And so the answer to this is, it's a horrible brace I just made. I'm at the end of the video. I'm getting tired and sloppy. -1 times I is -I, and that is the final problem with the final answer. I hope this helped out, and I hope you guys are having a great week, and you're staying on top of things, and keep on plugging away. We're more than halfway done with this class, and I hope things are going great, and you have a great day. Take care, and we'll talk to you soon. Bye.